That's a good size.
You sure?
Yeah.
Okay.
If you have this middle board up, because these lights here don't cast a shadow.
Okay. All the way up. Okay, great. Should I start? Can I start? Okay, great. Good afternoon. My name is Scott Dodelson. They asked me to talk about large-scale structure. This is my fourth time here, third time lecturing. I love it here. I hope you guys love it. You know by now to interrupt me and ask questions and stuff. The goal is to first talk about background cosmology. I've talked a little bit to the other people who've lectured so as not to duplicate what they've done, but I think it does make sense for us to spend a little bit of time going through that today. Tomorrow we'll do perturbation generation. No one else is doing inflation, so let's spend some time on that, how you generate perturbations, how they evolve. Most importantly for us, we're interested in how the perturbations, how the large-scale structure depends on physics. Stuff like neutrinos, dark energy, etc., because that's what we're interested in. And then the last two lectures will be how we probe them. And on the wiki, I put in a link to a Bitbucket site where you can download, install, and run 17 demos on Cosmosis, so you could be analyzing data by Thursday. So I strongly recommend you do that. It's very simple on any platform. Okay, any questions? Okay, good. So let's start. So GR. Let's do a quick thing on GR. So there's a metric, and so you know what that is. The metric essentially defines distances, physical distances, in terms of coordinate distances. So, for example, latitude and two cities different by a given amount of latitude are different distances from one another depending on their longitude. Right, and that difference in distances is determined by the metric on a sphere. So you're familiar with that. You know that you can raise. So by the way, you're not going to learn GR from this, but you are gonna. You'll know it, I assume, or anyway, even if you don't know it, you'll learn how to use it. So anyway, so the raising, lowering, the inverse of the metric is satisfies G mu nu. G nu beta is equal to mu beta. So that's just the inverse with upper indices. And you lower and raise indices with the metric. So for example, T mu nu, the stress energy tensor, is equal to G mu alpha times T alpha nu. Right? You just lower and raise with the metric. So that you know. The other thing, how am I going to do this? The other, so let's keep on going. You know about Christoffel symbols. So all of this has nothing to do so far with GR. It's just the way we talk about space. Right? This could be applied to just on those two cities on a sphere. We could define metrics, and we can raise and lower things like this. And similarly, any kind of space has a Christoffel symbol associated with it. And in terms of the metric, that Christoffel symbol can be written as follows: 1/2 times the inverse of the metric, alpha beta, times the derivative of the metric g mu beta with respect to x nu. And this derivative we'll call g mu beta comma nu. Okay? So that's just the convention we're going to use. And there, the second term here, therefore, can be written compactly as g nu beta comma mu. And then you subtract off g mu nu comma beta. So that is the Christoffel symbol, which we'll use it to construct a quantity that quantifies the curvature of space-time. And the first part of that is the Ricci tensor. So the Ricci tensor, so here I don't remember it. The Ricci tensor can be written in terms of the Christoffel symbol as gamma alpha mu nu comma alpha minus gamma alpha mu alpha comma nu. So those are the first two terms. And then there are two more terms plus gamma alpha beta gamma beta mu nu. And then minus gamma alpha beta nu gamma beta mu alpha. So that's the second, you know that. This is called the Ricci tensor. And then the Ricci scalar is just constructed by contracting this with the metric. So the Ricci scalar is defined to be g mu nu contracted with r mu nu. So that really has nothing to do with GR. That's just the way we talk about the geometry of space and time. There's one formula that takes all this stuff and makes GR, right? And that formula is the Einstein-Hilbert action. Let's do it like this. That didn't work. Have you? Okay, so the Einstein-Hilbert action reads like this. It's the integral d4x, the square root of the determinant of the metric. So g with no sub or superscripts is the determinant of the metric. And then the part that encodes the geometry is the Ricci scalar divided by 16 pi times Newton's constant. And then there's plus the coupling to the full matter of all stuff. So that's the Einstein-Hilbert action. And all you need to do to get all the, this is the T-shirt equation that gives everything. And it relates geometry to matter when you minimize that action. So for example, if you minimize this action with respect to the metric, then you get Einstein's equations. That's when you minimize that action with respect to the metric. When you minimize this action with respect to the position of a point particle, then, so these are Einstein's equations. If you minimize, so this is with respect, minimizing the action with respect to g mu nu. If you minimize the action with respect to the position of a point particle, then you get the geodesic equation. Where this lambda thing is just a parameter that monotonically increases along the path of the particle. That's it. That's GR. Any questions? Okay, so you guys are all experts in GR. All right, good. So let's leave this, and let's now do our first application of GR. So it looks like the best way to do this is to do the inner one first, right? I should have learned that. Okay. It used to be in a different room. When did they switch rooms? Oh, really? Okay. I was always in the room across the way. Okay, so let's do our first. So that was number one, GR. Number two, let's do this. Let's apply this to you've heard this term before, the metric that describes cosmology, which is a homogeneous isotropic spacetime, the Friedmann-Robertson-Walker metric. So that metric, we're going to do it in flat space. So the metric is it's pretty simple. G00 is equal to -1, and the spatial, and so there are 4 indices. G mu nu, I should have said it's 4. Alpha. All these Greek indices go from 0 to 3, and if we're using Einstein summation convention, so repeated indices are summed over. The Latin indices go from 1 to 3. So they're the spatial indices. And these spatial indices, the metric for the FRW metric is diagonal. So Gij then is therefore just equal to delta Ij. And if that was it, that would be Euclidean space. That would just be the simple normal stuff. But the universe is varying with time, and that's encoded in the metric by this scale factor, which you've seen. And the simplest way to think about that is to imagine a coordinate system. Remember, coordinates don't tell you anything about distances, where the difference between coordinates is, say, 1 meter. And this is at some time t1, the scale factor is a1, and if the coordinate distance is 1 between each of these points, then the physical distance between each of those points is a1 times 1 meter. And then at some later time, these points have gotten further away from one another, and the same 2 points are now separated by a physical distance a2 meters, right? And that is the notion that a2 is greater than a1 is equivalent to the statement that the universe is expanding. You've seen this metric a couple times already, I think. So once you've seen it with the perturbations put in, and then once you've seen it without the perturbations, and then I think Nalima showed you the perturbation equations that you get if you apply Einstein's equations to that metric, right? We're not going to do that, or at least I think she showed you that. We're not going to do that in full gory detail, but I do think it's worth our while to walk through a pretty simple example applying this to these equations, just so you'll be comfortable doing it to the more complicated thing that Nalima showed you. Okay, so let's do it for this relatively simple thing. I think Neil showed you the result, which is the Friedmann equation. Let's derive the Friedmann equation by applying Einstein's equations to this metric. Okay? All right, so let's do that. So in order to do that, what we have to do is we have to construct we have to write down Einstein's equations, and let's just look at the time component. Of Einstein's equations. So that is R00. And then it's minus 1/2 G00, but G00 is minus 1. So that's just plus 1/2 times the Ricci scalar is equal to 8 pi G. And then the time component of the stress energy tensor is just the energy density. So we're getting close. We have the right-hand side of this equation, the energy density. And now we just have to express these quantities which encode the curvature in terms of the scale factor. Okay, so in order to do that, we have to use this equation, that equation up there, which means the first thing we have to do is compute the Christoffel symbols. So it turns out that's not that difficult. There are only 2 non-zero Christoffel symbols. Let's walk through them. The first has an upper index 0 and 2 spatial lower indices. And that is equal to, I'll come over here and look at the Christoffel symbol. When the upper index is 0, since the matrix is diagonal, this index beta, since the metric is diagonal, this index beta that we're summing over, that's got to be equal to 0. So that means every time we have here a 0, beta we have a 0. So this then just becomes, but then this vanishes because it's G, a spatial index times a temporal index, that's 0. Right? And similarly here, this is a spatial index times 0, that's 0. So the only term that survives is this term, and it's the time derivative of the spatial part of the metric with the minus sign. So it's 1/2, then it's G0, 0, and then there's a minus sign, the derivative with respect to time of Gij. Right? That is what this Christoffel symbol is equal to. The time component of the metric is equal to -1, as is its inverse. So that kills that minus sign. And this Gij is just delta ij times a squared. So we can very quickly do that. We just write this as equal to, there's a plus, 1/2, the derivative with respect to time, a squared of t times delta ij. Okay, and so now when we take this derivative, we'll get a 2a times a dot. And I think you've already seen this. I'm going to write that as 2a dot times delta ij. But I think you've already seen that in cosmology we tend to define the Hubble rate, which is a dot over a. So let's write this as 2a, sorry, it's not 2, because this is the half. So this is just a squared h delta ij. Do you agree? Okay. That's the first non-zero Christoffel symbol. The second non-zero Christoffel symbol has, again, one index spatial, but one lower temporal index and the other lower spatial index. And so in this case, we have a 1/2. We have the inverse thing out in front has a first index I, and that means its second index also has to be spatial. So the thing that's over there written as a beta is a spatial index, but it's a dummy index. Let's call it K, to remind ourselves that it's a spatial index. And then everywhere we see a beta on the bottom there, we'll just call it K. Now in this case, the K thing, the derivative with respect to xk vanishes. Why? There's no spatial dependence to the metric. So the only thing that's not going to vanish is the one term. Remember, there's two indices in the bottom. One is spatial, one is temporal. The only one that's not going to vanish is the time derivative. So the only thing that won't vanish here is the derivative with respect to time of g kj. Right? So that is equal to, what's the inverse of, what is g superscript ik? Great. So that's equal to delta ik over 2a squared. And then it's the derivative with respect to time of delta jk times a squared. Right? So the delta jk, when you combine that, when you sum over k, that just leads to a delta ij. Right? So that's just going to be equal to delta ij. And then when I take the derivative of this, I'll get a 2 that kills that 2. And then I'll get an a dot over a. So I just get an h. Pretty simple, right? Because this gives a 2, which kills that. A kills one of those things, and then I'm just left with a dot over a. Questions? Okay, so that's the Christoffel symbol. That was the easy part. Now let's do the Ricci tensor. So we want to look at R00, the time component of the Ricci tensor. All right, so we look at this, and the first term up there is going to have a gamma 00. That's no good. That goes away because there's no remember I said there's only 2 that are non-zero, and both of them have at least one spatial index. So we're good with the first term. Let me get rid of this. Do I need this anymore? No. The second term here, though, is important. It's got this complicated thing. So this is equal to minus gamma. And so they're both spatial. This is the derivative with respect to time. This is a temporal thing. This has got to be a spatial thing in order for it to be non-zero. So this is going to be gamma I, 0, I, comma 0. Do you agree? That's that term. This term has a 0, 0 again, so we can ignore it. That's good. And then this term is non-zero. So you have to look at that minus term again. And that gives a minus. And again, because there's one, in each case there's one temporal index, all the other indices are spatial. So it's going to be I. It's symmetric in these lower indices, so if I'm mixing them up, it doesn't matter. So it's I. If it's I, then K0, and then gamma K I0 or 0I, whatever. Okay, so that is the time component of the Ricci tensor. Okay, this thing we know. This is the derivative with respect to time of this guy, but with the i's contracted. So what's delta II? 3. Good. So it's equal to minus 3, the derivative with respect to time of the Hubble rate. So that's easy. And the second term is minus. And then both of these guys come from over there. So I got a delta IK and another delta IK. So that's going to lead to another factor of 3. And then it's just h squared. So this is 3. So let me just pause for a second and compute the derivative with respect to time of h. That is equal to the derivative with respect to time of a dot over a. When you act on the numerator, you get a double dot over a. And when you act on the denominator, you get a minus sign because it's the denominator. You get a 1 over a squared. And then the derivative with respect to time of a, which is a dot. So you get a minus a dot squared over a squared, which is h squared. So it's a double dot over a minus h squared. So this will prove useful to us. So the derivative with respect to time of the Hubble rate is a double dot over a minus h squared. Let's plug this in to get r0, 0 is equal to minus 3 times a double dot over a minus h squared. And then I think this is a minus sign. Minus 3h squared. So this h squared cancels that 3h squared. So we're just left with r0, 0 is equal to minus 3 a double dot over a. So on the one hand, this looks great because we wanted to solve the Friedmann equation. We've already gone through GR in 10 minutes, and we're almost done with the Friedmann equation because we have r0, 0. On the other hand, the Ricci scalar requires us to compute all the other components of the Ricci tensor. So that's the bad news. All right. Ready? Questions? Okay, so what we need is the spatial component of the Ricci tensor. It turns out well, it turns out, if you think about it, the Ricci scalar is this thing, right? So since the metric is diagonal, the only thing it depends on is r0, 0 and r spatial. Any temporal spatial thing, even if it was non-zero, which I don't think it is, it can't be, it wouldn't contribute here. So we're safe. All we have to do is compute this one thing, and then we're done. So that turns out to be a little bit difficult. I should have spaced the board. Maybe I'll do that. Yeah, let's do that. Let's work over here on this thing. You know all this, so we're done with this. Okay, so this is what we wanted to compute. We want to compute Rij. And so this thing over here, this is non-zero as long as because it's got two spatial lower indices, as long as its upper index is temporal. And then the derivative is temporal, so that's good. So this is the derivative with respect to time of gamma 0 ij, which is non-zero. That's the first one. This term over here, though, does vanish because it's got a spatial derivative in it. And there's no spatial derivatives in this metric. Now, again, the reason we're doing this is it's so fun, but also because we want to prepare ourselves so that when you put in perturbations to the metric, you better just go through the same thing. It'll just be a slightly longer problem. So in that case, the perturbations to the metric, as Nilima pointed out, do depend on space. So when you put that in, you'd actually have to, you have to include a lot more terms. Okay, but in that case, it's pretty simple. So and now let's look at this thing over here. So there's the two spatial things over there, which means that this guy is temporal. That's temporal, but these two are spatial. So that actually contributes. That's a plus gamma I 0 I gamma 0. Sorry, this is a thing we're summing over. Let's call it K. Gamma 0 ij. So that's the second term. And then the third term, so there's one spatial index in both of these places, right? So alpha can be, if alpha is temporal, beta is spatial. If alpha is spatial, beta is temporal, right? So, but it turns out both of those terms contribute the same. So let's just do one of those things, and I'll put a factor of 2 there. So there's a 2, and then it's gamma. Let's choose alpha to be temporal, 0. Let's call beta k again. Nu is j, I guess. And beta is k. And nu is I, and alpha is 0. So that's it. So that is the spatial part of the Ricci tensor. Okay, so we can plug this in. This is the derivative with respect to time of delta ij times h times h. Is it h or h squared? Ha squared. For this one. Good. Good. Thank you. And then this term, okay, when we contract this guy, we'll get a 3 again, right? Because this guy had the delta ij in it. So this will be a 3. And then here it was just an h, right? Sorry, let me just remind myself. What happened? That's just an h. Okay, good. So so this is just an h. This is just 3h. That's the first term. And it multiplies this thing, which is delta ij times a squared h. Do you agree? Okay. And then we subtract off twice. So this thing over here is delta jk times a squared h. And this thing over here is delta ik times h. And that's it. The whole thing here, after you contract this, is equal to delta ij. So the Ricci tensor is diagonal. And then we have the derivative with respect to time of a squared h. Let's hold off on that for a second. This is 3a squared h squared minus 2a squared h squared. Right? Yeah, that's right. So it's just 1 a squared h squared. Is that right? Do you agree? Did I get the signs right? Did I lose any factors of 3? Looks okay? Okay, let's try it. So then this thing over here, when we act on the scale factor, we have a factor of 2a dot h. And when we act on the h, we know what that is. It's got an a squared out in front. And then it's a double dot over a minus h squared. So the whole Ricci tensor, spatial part of the Ricci tensor, this term over here is got an a dot in it, so we can replace this thing by another a squared h. So there's another a squared h squared term there. So what do we got? We got delta ij, 2a squared h squared minus a squared h squared. This is 1 plus another 1. So I think it's 2a squared h squared. And then I think that's a plus a double dot. Let's see if that's right. Did anyone find a mistake? I think that's right. Good. Okay. So we're ready. So now we're ready to just finish it off. Okay, so we have the Ricci tensor, and we want to compute the Ricci scalar. That goes into Einstein's equation. So that is equal to G00 R00 plus Gij Rij. G00 is minus 1. We know what R00 is. It's that thing, so it's minus and minus is plus 3a double dot over a. That's the first term. And then this term is a plus. Gij is delta ij over a squared. And then the Rij is this thing. So it's got a delta ij times 2a squared h squared plus a double dot. So the a double dot over a thing gives, this contracts to give a 3, right? So the a double dot terms give a 6, don't they? 6a double dot over a. And then these two terms contract to give another 6, and it's just h squared. Let's check that. That's right, too. Okay, we're almost home. So let's finish it up. So we want to write down now Einstein's equations, which tell us that R00, which is minus 3 a double dot over a, minus 1/2 G00, which is plus 1/2, R, which is right there, 6 a double dot over a plus h squared is equal to 8 pi g rho. The a double dot 3 plus cancels the minus 3 a double dot. So we're just left with, this is a 3, let's move it to the other side, and you get h squared is equal to 8 pi g rho over 3. Great. So we did GR and the Friedmann equation in a half hour. We're on a roll. Any questions? Okay, good. So let me make a couple of observations. I suspect these have also already snuck into the lectures. The first is that today it turns out that both of these quantities, the Hubble rate and the energy densities, evolve with time. And so we like to label the values at specific times. Their values today are designated with the subscript 0. So today we have the equation that h naught squared, its value today, is equal to 8 pi g over 3. And we label the density today the critical density. So this defines the critical density. And that, I think Nalima gave it to you, in whatever, 10 to the minus 29 grams per cubic centimeter. That's a number. Maybe for particle physics, it's more useful to think of, this is 10 to the minus 33 eV roughly. This is 1 over m Planck squared, so it's about 10 to the 19th GeV, so it's about 10 to the 28th eV. So it's the geometric mean of 10 to the 28th and 10 to the minus 33 eV, right, squared. So it's about 10 to the minus 5 squared. So it's about 10 to the minus 10 eV to the fourth. That's a rough sense. The energy scale then, if you put the whole thing in quantity to the fourth, is about 10 to the minus 2, 10 to the minus 3 eV quantity to the fourth. That's in particle physics units, right? Anyway, so this is this thing you've seen. And we like to, instead of giving energy densities of things like in units of grams per cubic centimeters, we give them in units of this critical density. So we define the energy density of a given species by its energy density in units of this critical density, which is just it's just a different unit, really. Okay. The second point is an exercise, which I'll call capital E. So this assumes that the universe is flat. If you want to generalize this to a metric, to the following metric, where the invariant distance is equal to minus dt squared, same thing, plus a squared, same thing. But if you want to introduce curvature by saying the radial distance has this kind of weird factor in it, I don't have it with me. It's omega k h naught squared r squared plus r squared d solid angle squared. So this is the metric if the universe were curved. So omega k quantifies, one way to think of it is the curvature energy density in units of the critical density. So as you probably know from NLEMA, we actually have very tight bounds on this. It's less than a percent or so. So that's why most of us are comfortable neglecting it. But if you're interested in working this out, you can work through this, and you should, let's do this, I'll write this once. This is an exercise. You should be able to show, doing the exact same steps, although slightly more complicated metric, you should be able to show that the Friedmann equation generalizes to a dot over a squared is equal to 8 pi g rho over 3 minus h naught squared omega k over a squared. Yeah. What is the value? It's known to be less. Its magnitude, its amplitude is known to be less than 1%. That's how accurately we've measured it so far. Other questions? Yeah. Right. So, if the universe had positive curvature, then this term would be positive, and that means very early on the energy density, as we'll see in a minute, was very high. So this term dominates. But as the universe expands, it gets more dilute. So this energy density drops, and when it reaches this value, then the expansion rate will stop, and it will turn around. It will begin to contract again. So in a universe with positive curvature, the notion is one signature of that is the universe would expand and then contract again. Oh, sorry, here? I see. Okay, good question. Right, good question. I don't know the answer to that question. It's a good question. I guess... Right. So this is an infinitesimal equation. Maybe it has to do with the fact that any r larger than is effectively the horizon is not an observable quantity, but that's not a good answer. So let's just. It's a good question. I should give that question deserves a better answer than I'm giving it. So, what happens if that term becomes negative? Doesn't become it. So okay. Sorry. So you're saying r has a finite value. Right. Good point. Okay, good. Thanks. Better answer. There you go. So in other words, R has a maximum value of 1 over omega k h naught. So it's got a finite value. Yeah. Thank you. Other questions and answers? Okay, good. Third point is okay. So we did the time equation. Here's another exercise for you. If you do the space component of Einstein's equations, then you should be able to combine it with the Friedmann equation and show that a double dot over a is equal to minus 4 pi g over 3 times rho plus 3 times the pressure, where the pressure is the spatially diagonal element of the stress energy tensor T mu nu, which is assumed to be isotropic. So all 3 components are supposed to be the same. So this equation tells you that what you'd expect from gravity, that it decelerates. That is, we expect if the universe is expanding today, the change in the expansion should be negative for normal stuff. The universe should be decelerating. Okay, that's the end of part 2 of this. Any questions about that? Okay, a quick foray then into part 3, which is the constituents of the universe. We now have a language to describe the what's in the universe, and let's just quickly run through what you've already heard. The fraction of the total matter that's in of the total density that's in matter is about 0.315, plus or minus about 1%. Of that matter, as you've heard today several times, only a small fraction is in baryons. So the fraction of energy that's in baryons is known extremely accurately, and that is known to be less than the total matter. So this right here, these constraints come predominantly from the microwave background, and they're the strongest argument for the existence of a non-baryonic dark matter, right? Because the baryon density is a factor of 6 or 7 lower than the total matter density. I screwed this up again. Okay, so that's that. There are also photons in the universe. You heard about those. I just want to write them a slight. I think Nalima wrote this, but let me just write it again just for emphasis. There are also photons called in the context that comprise the microwave background. And the energy density of the photons in the cosmic microwave background, which is a black body, can be computed. So I think Nalima gave it to you in terms of some astrophysics formula, but you should all compute this. So this is another exercise. And what you do is you just do it, and you don't need to memorize anything. You know that photons have two spin states, 2 polarization states. So you put a factor of 2 in, and then you sum over phase space. And phase space means you sum over all momenta, dividing by the volume of momentum. So H bar and C are 1. And then you know so that just sums over all things. And then you count the number of particles that are occupied in each state. And we know what that is for a Bose-Einstein distribution. It's just e to the energy, but the energy is just the momentum, divided by the temperature minus 1. So that's the number. That's the occupation number of photons. And then you multiply by the energy, but the energy, again, is just the momentum. So this is a trivial integral. You should at least have done it once. This is equal to pi squared over 15 times t to the 4th. So you should show this. And you should also then take this number here and know that the temperature today is 2.725 Kelvin, which is equal to 2.35 times 10 to the minus 4 electron volts. So you know what that is. You can compute the energy density of the CMB, and you should be able to show that the energy density, there's the value today, of photons today in units of the critical density is very small. It's 5 times 10 to the minus 5. Okay, questions about that? Good. Fourth constituent of the universe is neutrinos. We're going to get to that in shortly. And it turns out that the energy density in neutrinos is less than 1% of the critical density, is less than 1% of the critical density, and but greater than 1/10%, somewhere in that range, depending on the mass of the neutrinos. So that's small. So what we have is with these known things, the known matter, all the baryons, just make up 5% of the energy density. The dark matter makes up an additional 25%. That puts us up to about 32%. Photons make up essentially nothing. Neutrinos make up essentially nothing. But we know that the universe is flat, which means the sum of all these omegas has got to be equal to 1. So that implies that there's something missing. And that something is what we call dark energy. And dark energy has a value just by this thing of about just summing up these things of about 0.68 of the critical density. We know one more thing about the dark energy, or you already do, just simply by that exercise that you'll do tonight, because you've heard that the universe is actually accelerating, not decelerating, right? And so what that means is, sorry, let's just leave it like that for now. Sorry, that's what we know for now. Okay, questions about that? I think you've seen this. All right, next thing. Item number 4 is the evolution of stuff. So this is what the universe looks like today. How did it look in the past? So a number of people have hit on this, but we've built up the machinery to analyze it quantitatively. So let's just work through that. So what we'd like to do is understand how the energy density of a given species evolves with time. And we can actually do that. We can just take the Friedmann equation, which has the energy density in it, and differentiate it. So let's take the derivative with respect to time of the Friedmann equation, which is 8 pi g over 3 rho is equal to h squared. So let's just differentiate that equation. So when we do that, we get 8 pi g over 3 rho dot is equal to 2h times h dot. But h dot, we know what it is because we computed it before. It's a double dot over a minus h squared. So now what I like to do is use that space-space equation and the Friedmann equation to write this to tell us how the energy density evolves with time. There's another way to do this. You can write down the stress energy tensor and enforce the constraint that it's covariantly conserved. So you can do it 2 ways, but you get the same answers. This is just a simple way to do it. All right. So this is let's plug in this stuff. The right hand side then is equal to 2h. Now, a double dot over a, we said, is equal to minus 4 pi g over 3 times rho plus 3p. That's what a double dot over a is. And then you subtract off minus h squared. So now I want to introduce a definition. Let's define the equation of state W to be the energy density divided by the pressure. Then this term over here looks very much like the right-hand side of the Friedmann equation. So if we just multiply it by a factor of 1/2, then we get out h squared. So then I claim that this term is equal to 2h. The term in brackets has a minus sign out in front. If I put in a factor of 1/2, then I've got 8 pi g over 3 times rho, which is equal to h squared. And this thing over here that's multiplying it is 1 plus 3 times the equation of state W. And we're subtracting off from this another h squared. So that's what this right-hand side looks like. The left-hand side, if I multiply and divide by 3, by rho, I get 8 pi g rho over 3. That's another h squared. So then all these h squareds go away. And what I'm left with is rho dot over rho. I've multiplied and divided by rho here. Is equal to 2h. The h squareds are gone. So then it's minus 1/2. Minus 1 is minus 3/2. And this thing is another minus 3/2 times w. So this says that derivative with respect to time of rho, of the log of rho, is equal to minus 3h times 1 plus w. So that tells you how a species, the density of a species evolves with time. Questions about that? Okay, so when you solve this, what you find out is that the energy density of a given species is equal to its value today times the exponential of minus 3 times a to the minus 3 times 1 plus w. So you can just check that that solves that, or you can just solve it. Questions? Okay, let's do 3 quick examples of this. For matter, non-relativistic matter, the pressure has an order of magnitude roughly of order T over m. The pressure over the energy density. The pressure is the kinetic energy, so it's just the temperature, divided by the energy density, which is the pressure per particle is T. The energy per particle is m. So T over m for non-relativistic matter is very small. So W is effectively 0 for non-relativistic matter. And what that implies is that the energy density of non-relativistic matter scales as a to the minus 3. And that makes sense, right? If the room is doubling in size, then the energy density would fall as the scale factor cubed, as the volume. For radiation, for relativistic particles, the pressure is equal to 1/3 of the energy density, and therefore W is equal to 1/3. And that means the energy density scales as a to the minus 4. And that has an important ramification. Well, 2 important ramifications. The first is the energy density in radiation today is small, but as you go back in time, since it scales as a higher power as the scale factor, when the scale factor was much smaller, the energy density of radiation would have been much bigger, right? So even though today the universe has much more matter than radiation, early on it was dominated by radiation. So that's why Neil, a few hours ago, assumed that the energy density was dominated by just T to the 4th, right? That's the first point. And the second thing to notice is that since the energy density is proportional to the temperature to the 4th power, and also the scale factor to the minus 4th, this tells you that the temperature falls as 1 over the scale factor. Right? And this is this is a slightly more rigorous way of proving something that you know intuitively. As the wavelength of a photon expands, its energy, which is the temperature, the energy per particle is the temperature, its energy is going to go down by a factor of 1 over a. Right? So that's a simple way of thinking about it. And the third example is this dark energy. So the one thing we know about dark energy is the universe is actually not decelerating today. You read about it in the newspapers. So it's accelerating. That means that right-hand side over there has a minus sign out in front. It's got a rho, which is positive, times 1 plus 3w. So that means W of the dark energy has to be less than minus 1/3. So it's very strange stuff, and you probably know that one possibility for a dark energy is a cosmological constant that corresponds to W equal to -1. And if W is equal to -1, it just tells you that the energy density remains constant for all times. So this enables us to put up a little chart that I don't think you've seen yet, which is, let's start today when the scale factor is equal to 1. And let's go back in time. And let's plot the energy density of a given species divided by the total energy density. So today, most of the energy density is in terms of this dark energy stuff, right? And it's about twice as much as matter. So this is dark energy today. It's got about twice as much matter as matter. And radiation is way down here. The CMB, the radiation is way down here. But as you go back in time, the energy density of dark energy remained roughly constant. Whereas the energy density of matter shot up as e to the -3. So in the very recent past, matter was actually the dominant constituent. And dark energy was effectively irrelevant. Maybe it goes e to the -3, I guess. So when that's 10 to the -3, this is 10 to the -3. So dark energy played almost no role at early times. So that's why, for the most part, the CMB that Nalima talked to you about, which takes place over here, isn't really sensitive to dark energy, unless there's something really weird going on with dark energy. So that's matter. And then radiation, this matter scales as e to the -3. Radiation goes up faster, e to the -4. So at some point, you can calculate it just by the ratio. The relative density of these things is their relative density today multiplied by a factor of a, because one goes to a cubed, one goes to a to the 4th. So at some point, radiation is going to win. I think Nalima quoted you the exact number, but let's not focus on that now. Let's just point out that at some point, the matter is not going to be important anymore. At early times, radiation is important. So this is I think this is a useful thing to have in your mind as you walk through the different things. So for example, you heard today about dark matter, when the dark matter was produced, and dark matter annihilation. That was at early times when the universe was radiation dominated. That's why Neil was able to take rho goes to 2 to the 4th. Coincidentally, what Nalima was talking about when recombination happened about 10 to the -3, matter and radiation were about the same. That's just a coincidence, but that's about true. That's true. Some textbooks say there's a fundamental thing about that, but it's just a coincidence. Right? So that just happens to be the thing. If you want to learn about dark energy, you're not going to really learn much from the CMB because it probably wasn't around then. So really you have to do experiments that probe the large-scale structure of the universe. Yeah. Great. Okay, good. Okay, good. So we'll get to that. Good point. So the CMB probes this thing. The CMB is a picture of the universe when it was 400,000 years old, except it's not, because there are two things that distort it. One is CMB lensing, and the other is the Sinyavsky effect, the fact that it scatters off hot electrons. So both of those things enable the CMB to prove useful as a probe of dark energy. But really, it's not because we're probing that epoch. It's because we're using it as a source to probe this epoch. So it's really still here we're probing. So that's kind of this thing. Yeah. Okay. Other questions? Yeah. Yeah. So good question. We know that the curvature energy density just in the equation goes to e to the -2. So based on that, you can just do it and figure out what W is from that. Yeah. Yeah. I think. CMB stuff? So the CMB, if the textbook story is the CMB comes to us, it's a picture. The photons travel freely through the universe, and we see the universe as it was when it was 400,000 years old. And that's roughly true, but as Nalim pointed out, the photons get deflected by large-scale structure along the line of sight, and therefore the way those photons get deflected tells us something about the large-scale structure at these late times. And so that in itself actually doesn't give you that much information about dark energy, but I hope we'll get to this. When you cross-correlate that information with other information about, for example, in tomographic bins of galaxy surveys, you can see how rapidly structure is evolving with time. And that does give you information about dark energy. So that's the lensing stuff. And then the other thing, the scattering off hot electrons tend to exist in galaxy clusters. And the galaxy clusters are very rare objects. And the rate at which they form also tells you how rapidly structure grows. So those two things together are actually very powerful probes of dark energy using the CMB, but not at the time when the CMB was released. Yeah. Yeah.
Would like to ask a question that Kevin asked.
Yeah, sure.
But I want to hear your answer. There is like
You know the answer, you just want to see where I'm right. Okay, okay, go.
In reality, the answer wasn't that good, but I want to repeat it. Is there an upper limit and a lower limit for double loop
W. Oh, okay, good. I mean observationally.
or like theoretically?
Okay. Yeah, so for a long time people... Okay, so first of all, you should know by now, we're just making W up, right? We don't know what dark energy is. So you can write down a scalar field model, and in most scalar field models, W should be greater than -1, or else it leads to ghosts and weird kinetic energy terms and stuff. So that's a theoretical thing that people can evade by concocting crazy models. So phenomenologically now, people tend to just fit for W without imposing those constraints. And phenomenologically, there is not the... So W is consistent with -1, but in a weird way, maybe we'll get to that later. But the phenomenological constraints now are consistent with -1. But if we find if you could be in some weird part of parameter space where it's actually quite a bit different, just the other parameters are different as well. Once you open up, you're introducing a new parameter with W. So it could be that omega matter is actually different than that, and W is weird. So that's
Also can be like low.
right. So W cannot be 2 unless the equations that we've written down are wrong, right? Because we have this simple equation that says A double dot is negative.
But I'm not talking about dark matter. I'm talking about
Dark energy. Yeah, you mean any species. Okay, good. Right. So nominally, if for particles, for normal particles, so I think the answer is you can concoct models that have infinitely large equations of state. Isn't that right? Like Steinhardt stuff and everything. But if you're normal, then if you think about just normal stuff, like if you're a condensed matter physicist, then the energy density is the sum over phase space of the energy, and the pressure is the sum over phase space of p squared over 3e. Right? So that's why the energy density of radiation, where P and E are the same thing, so there's just E over 3, is a third, right? So how big can you get this? Well, if you have a massless particle, you can get W as big as a third. But it's very hard to see how you can get it bigger than a third, right? So because generally, so play with these things, it's very hard to see with normal particles that you can get a W greater than a third. The bound normal particle seems to be between 0 and a third. But then you introduce like more complicated things, you can get more complicated.
for example,
Right. If you're just thinking of excitations, no. If you think about scalar fields, then the pressure is the kinetic energy minus the potential energy, and the energy density is with a plus sign. So the ratio of those two, play around with that and see the range. So that's yeah. But then so that's,
the maximum I've seen from 1
Right.
is 1, but I've never seen people go to 2 or
Yeah, I suspect many of you here know more than I do about that. Yeah, but there have been, I mean, there are people with either multi-field models or complex kinetic terms that I think relax those bounds. But I think you're right in the simple one-field quintessence thing. Those are the limits. Yeah. Good. Other questions? Okay, so we've got about 10 minutes left. But I want to get to neutrinos because they're going to have an impact on large-scale structure. We'll be able to learn something about the masses of neutrinos by looking at large-scale structure. So I just want to convince you that they exist in the universe and that we know exactly actually how many there are. So let's walk through that. Imagine a universe early on, very early on, when the temperature was very large, bigger than the so this is the last thing I wanted to talk about, the neutrinos. The temperature was bigger than the mass of the electrons. So at those early times, as we've seen, the universe is radiation dominated. So what do you have? You have electrons, you have positrons, and you have photons. And let's imagine you have no neutrinos at all. Okay. So then Nalima actually pointed out a very key principle, which is if you have a reaction whose rate is greater than the expansion rate, then the particles involved are driven to equilibrium. So you learned about this in essentially Neil's thing this morning, I suspect, was saying we have the dark matter particles, they're in equilibrium as long as they can find something to annihilate with, right? And so they get exponentially suppressed. But then when they stop finding something, being able to annihilate rapidly enough, they drop out of equilibrium and they freeze out. Right? That was what we were doing this morning. And that was precisely this rate. That is, the time at which the reaction rate for annihilation in that case becomes smaller than the expansion rate, that's the epoch at which the dark matter abundance freezes out. But that's part of that's one example of a general principle that the reaction rate greater than the expansion rate means that particles are driven into equilibrium. So back to our universe that has no neutrinos initially. Well, if there are no neutrinos, all there were electrons and positrons, you could have a reaction that looks like this. Right? This is a simple diagram you can draw. And you can calculate the rate for this reaction. So this is one of those things that you can just estimate very quickly. It's got two vertices with the electromagnetic coupling, roughly. So it's got it goes as alpha squared. It goes as the mass of the z to the fourth, because there's a propagator. And in order to get it dimensionally correct, this has got to have dimensions of mass. You put in the only mass in the problem. Since everything is massless, what's the only mass in the problem? Right. So it goes as the temperature to the fifth. That's the reaction rate. And the expansion rate is just the energy is 8 pi g over 3. Let's forget about that. And then it's got this g is 1 over m Planck squared. And rho to the 1/2. But rho, everything is relativistic, so it's just t squared. So as Neil pointed out this morning, it's just t squared over m Planck. So you see that early on, if you go to high enough temperatures, the reaction rate is going to be larger than the expansion rate. So even if God started the universe with no neutrinos, you would produce them via electron-positron annihilation, right? And in fact, you can just plug in numbers here and show that this ratio is equal to the temperature over a few MeV cubed. So that means when the temperature is above a few MeV, neutrinos are in equilibrium with the rest of the cosmic plasma, so they're produced. So there are roughly as many neutrinos in the early universe as there were photons in the early universe. Okay, what about today? Well, there's some differences, but two of them cancel out. Let's think about one generation of neutrinos. There's only one spin state for a neutrino, but it's got an antiparticle. So it's really got 2 degrees of freedom. Photon has two spin states, so that actually cancels out. Same numbers of degrees of freedom. Photons are bosons. Neutrinos are fermions. So that results in the fact that the number of neutrinos is slightly smaller because the occupation number, instead of being -1, is +1. So there are slightly fewer neutrinos than there are photons. And just go back to this integral over here. if I wanted to calculate this number density, I just would have done the exact same integral without this factor of the energy, right? So what that means is the number density of stuff, massless stuff, photons or neutrinos, goes as T cubed, right? So I have to put one other factor in here, and that is the ratio of the temperature of the, sorry, this is photons. The temperature of the neutrinos to the temperature of the CMB. Cubed. So that is the number of neutrinos. Now we know the number density of photons today exquisitely well, right? I wrote down 4 decimal points in the temperature, so we know it to like three decimal places. So the only thing I have to tell you is this ratio, and you know exactly how many cosmic neutrinos there are, and that will turn out to be very important. Yeah. Good question. You should if you want to calculate the energy density, but their number density, it's completely unaffected by that. Because their number density, think of the number density of particles in this room. The room expands with time. The number density, doesn't matter whether they're massive or massless, the number density is evolving the same way. Good question, though. Okay, so this ratio turns out to be a little bit more subtle than you would think, but it's a fun calculation, which we won't get to. And it looks something like this. Let's say you question? Yeah.
That's the question I always ask. They ask myself, sorry. It's that when you say, okay, we have neutrinos, right? What happened if Majorana react? Now the number will change. So, like, why we can say, oh, we can discover the nature of neutrinos with cosmology?
Okay, good. So there are, let's think of everything. You can, Majorana and Dirac is confusing, right? A Dirac neutrino is made up of 2 Majorana things, right? Okay, so let's think of the left-handed neutrinos. Those are the ones that are governed by that interaction. Then there are the right-handed neutrinos. Those are not governed by those interactions. So you have to ask yourself how those are produced, right? So if we think about it that way, then the ones I'm talking about are just the left-handed ones. And then it becomes a separate question, are the right-handed ones produced? And if they are, with what abundance? And that's a very interesting question, but that's not the ones, and it's possible in some models they're produced with the same abundance as the left-handed ones. But instead of saying Dirac and Majorana, let's talk about normal, normal, weakly interacting and non-weakly interacting. Good question. That's a very good question. That's obviously very important. Okay, so this is the temperature of the neutrinos. So so the temperature is big in this direction. So we said when the temperature is above, the mass electron volt is a half of an MeV. So above an MeV, photons and neutrinos and electrons have the same temperature. So if we were to plot the temperature, say, of the photons, so this is the neutrino temperature, just a straight line, because the x-axis is neutrino temperature, so the y-axis, if I'm applying neutrino temperature, is a straight line. So anyway, so that, that's not interesting. But the photon temperature is interesting. So the photon temperature is tracking the neutrino temperature because they're in equilibrium. Now they stop talking to one another at 3 MeV. What happens? Nothing. They stay exactly the same because they're both. It doesn't matter that the electrons and positrons and photons are talking to one another. They're all falling as 1 over A because they're all relativistic, right? So both neutrinos they've stopped talking to the photons, but they're still falling off at the same rate. So for a long time after 3 MeV, as the temperature drops, the photon temperature tracks the neutrino temperature. But then the electrons and positrons start to annihilate. And when they annihilate, they dump their energy predominantly into the photon gas, not into the neutrinos. So at that point, there's a little bit of a shift. And the photons get heated relative to the neutrinos. And after that happens, they just evolve the same way. Because after that happens, nothing affects either of them, and they're just evolving the same way. So there's a slight offset, which you can calculate. It turns out the temperature of the neutrinos relative to the photons is equal to 4/11 to the 1/3 power. So that does it. That number, which is a calculable thing, you plug in here, and you get exactly the number density of neutrinos today. And that's very important for 2 reasons. So that's one thing you can do. And the other thing you can do is you can also calculate the energy density of neutrinos while they are still massless. So let's keep them massless for a while, because remember, as long as the temperature is above an EV, they're massless, right? So during that epoch, their energy density, it turns out the difference between fermions and bosons is a factor, instead of 3/4, gives a factor of 7/8. So it's 7/8 the energy density of photons times this ratio, the neutrino temperature, which we've said over the photon temperature to the fourth power, right? Because energy density goes to the fourth power. So I think Nalima gave you this number. This turns out to be, when you multiply by 3 neutrino species, this turns out to be 68% of the CMB density. So that's important, because that enables us to determine precisely this epoch here, when the energy density of radiation is equal to the energy density of matter. Right? Because if you didn't do that, you get it wrong, because you'd be missed off by 50% or something like that. Turns out we know this number extraordinarily well. Do you know why? Because as we'll see tomorrow, before this time, the energy is dominated by radiation, so it's very hard for stuff to collapse. And after this time is when structure begins to form. So we know this number to sub-percent level. And so it's very important to get precisely the neutrino contribution. And Nalima gave it to you precisely, but that's where it comes from. Okay? So you now have all the ingredients to put it together to get Nalima's number. And the second, so that's for the energy density. So in terms of, now let's go back to your question. As the temperature drops, the energy density of neutrinos, so really the energy density is the sum over phase space, the square root of p squared plus m squared times the distribution function, right? So let me write that. Give me 2 minutes, sorry. So it's got this factor of 2 for the neutrino and antineutrino. You're summing over phase space. It's this Fermi-Dirac distribution, p over t nu. It's +1 instead of -1. And then for the energy density, it's p squared plus the mass of the neutrino squared, right? For each of 3 generations. But and then in the high temperature limit, I neglected this and I gave you the answer. In the low temperature limit, this just becomes a factor of the mass, and this is just a number density again. So we can just use that thing over there, right? So here's another exercise for you. You should be able to show that the energy density of neutrinos today that have mass in units of the critical density is equal to the sum of the neutrino masses divided by 94 electron volts times little h squared. Did you get little h? You did learn little h, right? So that turns out to be the answer. And a slightly more convenient way of saying that is it's the sum of the neutrino masses over 1 electron volt and about 0.011 or something like that. So I guess there's an h squared here. So that's it. And so the reason why this is important is that if neutrino masses make up, if the sum of neutrino masses is about an electron volt or so, then omega nu h squared can be about 0.01. But omega nu h squared of ordinary matter is about 0.1. So that means neutrinos, the fraction of the matter in neutrinos, in massive neutrinos, can be as large as about a tenth. And that will turn out to have significant impact on the distribution of structure in the universe. Okay. Questions? Yeah. Yeah, so the reason it's slightly off is, why is it slightly off? Right, good. So does everyone see the point, the question here? So what that ends up doing is slightly changing this number here. And so what people tend to do is write it as follows, in this very strange way that confuses people. They write this number, and then they multiply it by n effective over 3. And so what they do, that's just the definition of N effective. And the point that you just made is that the energy density is slightly larger than the naive value that assumes that they were didn't share at all in the heating by electrons, positrons. So N effective is 3.046. So it's like a 1% effect and stuff like that. So that's the point. And actually there are, what Limas pointed out, CMBS4, one of the things it might do is detect the deviation of N effective from 3. Measure 3.046. That would be quite amazing. Other questions? Yeah. Yeah. So then you just do a different thing. It would just be alpha squared T, right? So at that point, it's right. It would just be alpha squared T, right? That's right. So at that point, that's a good point. The very high temperatures, it's not obvious that neutrinos would be produced. You have to wait till the Z becomes non-relativistic. Yeah. Other questions? Okay, so we break, I guess.